Dear students, in our previous lectures we have discussed that the short transmission line, the medium transmission line and the long transmission line. Today we will continue those lectures and we will study the generalized circuit constants of the transmission line. For a four-terminal network, and the network has to be passive, linear, bilateral, the input voltage and the input current can be expressed in the terms of output voltage and the output current. And according to this definition of a four-terminal network, the transmission line is considered as a four-terminal network where two terminals are input from where the power enters and two terminals are for the output from where the power leaves. And the expressions for the input voltage Vs and input current Is or expressions for sending end voltage Vs or sending end current Is of a three-phase transmission line are given as Vs is equal to A into Vr plus B into Ir. Is equal to C into Vr plus D into Ir, where Vs is the sending end voltage per phase, Is is sending end current, Vr is receiving end voltage per phase and Ir is the receiving end current. In these two equations we can see that we have four unknowns which are A, B, C, D. These four unknowns are actually the circuit constants of our transmission line, and our today's lecture will discuss these four constants in short, medium and long transmission line. We will find the different values of A, B, C and D, and before going into it we have to study some important points about these four constants. These important points are: number 1, the constants A, B, C and D are generally complex numbers. The constants A and D are dimensionless, where the dimension of B and C are ohms and siemens respectively. And for a given transmission line, A will always be equal to D and A into D minus B into C will always be equal to 1. Next, now we will determine these constants values for the short, medium and long transmission line. First of all, we will find the values of A, B, C and D for short transmission lines. As we have discussed in previous slide, that the sending end voltage Vs and the sending end current Is of a transmission line can be expressed as these two equations, where equation 1 is for sending end voltage and equation 2 is for sending end current. For a short transmission line where the equivalent circuit is given in this figure, here you can see we have a sending end voltage A series impedance consisting of a resistance and inductance and a load, and the voltage across the load are VR. Here IS and IR are actually series current. Now in the short transmission line, as the capacitance is ignored, so the short transmission line will only have series impedance, which includes resistance and inductance. And according to the figure, we have these two equations, which means IS will be equal to IR, or the sending end current will be equal to receiving end current, and this is because of the fact that the circuit is simply a series network. And next value from the circuit will be Vs is equal to Vr plus IR into Z. Now if we compare equation number 3, equation number 4 with equation number 1 and equation number 2, where equation number 3 will be compared with equation number 2, or simply the values of IS and IS will be compared, while the value of Vs and Vs will be compared. So after the comparison, we can see that A will be equal to 1, B will be equal to Z, C will be equal to 0, and D will be equal to 1. And as we have discussed in the properties that A will always be equal to D, and A into D minus B into C will be equal to 1. Hence both of these properties have been proved in the short transmission line. Next we have medium transmission line. In the medium transmission line, we have studied two different methods. First one was nominal T method. In the nominal T method, we divide the impedance into two halves. One half is towards the sending end and other half is towards the receiving end, and the line impedance is lumped in between these two impedances. As you can see in this figure, we have Vs is sending end voltage, Is is sending end current. At this point, Is divide into Ic and IR, where IR is the receiving end current and VR is the receiving end voltage, and the voltage across this capacitance will be V1. Here the Y is showing the capacitance, admittance of the capacitance, and from this figure we have these equations where Vs is equal to V1 plus Is into Z over 2, where Z over 2 into Is is the drop in this branch, and V1 is voltage across this branch. So Vs will be equal to V1 plus this voltage, and V1 will be equal to Vr plus the drop in this branch, which is equal to V1 is equal to Vr plus IR into Z over 2. And next we can see from the figure that IC is equal to IS minus IR, or IS is equal to IC minus IC plus IR. And again we have IC is equal to V1 into Y, where Y is the shunt admittance, and from this we put the value of V1, which is VR plus IR into Z over 2, and we get this equation. And this equation is basically for the capacitance current IC. Now we have IS is equal to IR plus Y into VR plus Y into IR into Z divided by 2, and after putting the values we get this equation, and we name it equation 6. Next we substitute the value of V1 in equation 5, and with that Vs is equal to VR plus IR into Z divided by 2 plus IS into Z divided by 2. And next we will substitute the value of IS, and now we get Vs is equal to 1 plus Yz divided by 2 into VR plus Z plus Y into Z square divided by 4 into IR, and we name it equation number 7. Now we compare equation 7, which is the expression for Vs, and equation 6, which is expression for Is. We compare these two equations with equation 1 and equation 2, and for your ease the equation 1 and 2 are mentioned here. And after comparison we see that the value of A and D are 1 plus Yz over 2, the value of B is Z into 1 plus Yz over 4, and the value of C is Y. So, and next thing is A into D minus D into C is equal to 1. So our two properties are satisfied here, which were the value of A will be equal to D and AD minus BC will be equal to 1. The next method was nominal pi method. In nominal pi method, we divide the capacitance into two halves. First half is towards the sending end and other half is towards the receiving end, while the series impedance, which includes resistance and inductance, are in a series branch and lies between the sending and receiving end. And from the figure we have these equations where Z is equal to R plus JXL, which is the series impedance per phase, and Y is equal to J omega C, which is the shunt admittance, and Is is equal to IL plus IC2. These equations come from applying the KCL on this node. And next we have is is equal to il plus vs into y divided by 2. We just have substituted the value of IC2 and we got the value of is and we named the equation as equation 8. Next we have il is equal to ir plus IC1, and if we put the value of IC1 we get ir plus vr into y divided by 2. Now the expression for vs is equal to vr plus il into z, where vr plus the value of il is ir plus vr into y divided by 2 into z. We just have substituted the value of il in this equation, and now what we get is vs is equal to vr into 1 plus yz divided by 2 plus ir into z, and we name it as equation number 10. Now the expression for is will be this equation, and if we put the value of vs from equation 10 we get is equal to this equation, and this equation have in this equation we just have substituted the value of vs over here. Now what we get is this equation. This equation is basically for the sending end current, and to define this equation we have this equation which is labeled as equation number 11. Equation 11 is basically the expression for sending end current, while equation number 10 is expression for the sending end voltage. Now we have to compare these two equations, equation 10 and equation 11, with equation number 1 and equation number 2, and after comparison what we see is a is equal to d is equal to 1 plus yz over 2, the value of b is z, the value of c is y into 1 plus yz over 4, and the next thing is AD minus BC is equal to 1. Hence our both properties have been verified, which were A will be equal to D and AD minus BC will be equal to 1. Next we have long transmission line, which is solved by rigorous method. By the rigorous method, the sending end voltage and the sending end current of long transmission line are given by these equations, where Vs is the sending end voltage and Is is the sending end current, and the value of Vs is this equation, while the value of sending end current is this equation. We have to compare these two equations with equation number 1 and equation number 2, and after comparison what we see is the value of A is equal to value of D, which are cos hyperbolic under root of yz, and the value of B is under root z over y sine hyperbolic of under root yz. and the value of C is under root y over z, sine hyperbolic of under root by z, and the other property is AD minus BC will be equal to 1. Hence, our both properties have been verified here. Now, up to now we have discussed the unknown constants for short transmission line, medium transmission line and the long transmission line. Now, we will discuss an important term in a transmission system, which is surge impedance loading. Always remember that if a line is lossless, its series resistance and shunt conductance are taken as 0. The characteristics impedance now reduces to a real number with no imaginary part, and the real number will be equal to under root L over C, which has dimensions of ohms, where L is the series inductance of line in Henry and C is the shunt capacitance in Farad. And when the line is loaded by being terminated with an impedance which is equal to its characteristics impedance, the receiving end current will be IR is equal to VR over ZC, and for a lossless line, ZC, the receiving end current will be IR is equal to VR over ZC, where ZC is the characteristics impedance, which is a real number. Now, for a lossless line, ZC is purely resistive, and the load corresponding to the surge impedance at rated voltage is known as surge impedance loading, which is abbreviated as SIL, and mathematically it is given as SIL is equal to 3 VR into IR, or 3 the magnitude of receiving end voltage square divided by ZC, characteristics impedance. Since we know that the receiving end voltage is equal to the line voltage divided by under root 3, so the surge impedance loading in megawatts will become this equation, which is surge impedance loading is equal to the kV line rated whole square divided by characteristics impedance, and the unit of SIL will be megawatts. This was the topic of surge impedance loading. Hope you have understood the SIL. If you have any comments, if you have any questions, please feel free to ask in the comments. Hope you like this video. Thank you.